Okay, we're now going to look at nuclear fusion, which is the process of fusing two nuclei together. So we've already done fission where we split a large nucleus, but it's more common in the universe for small nuclei like hydrogen to actually join together or fuse and become a larger nuclei. Okay, so if you imagine sort of a H11 here and a H11 coming together, what you've got there is two protons and they've both got a positive charge. So obviously there is an issue in trying to fuse these together because they're both positive. And as they get closer, that coulombic repulsion, the electric force repulsion, is going to become extremely large at short distances. So normally they'll get so close, turn around and move away from each other. So to get these to fuse together, you normally need to have them going very, very fast. So they've got to have a very high kinetic energy, which means they're going to have a high temperature. So there's often a thing called a critical temperature they talk about here, which we don't really do in this course, but it is there. Okay, so you need really high heats here. So we're talking about several million degrees Celsius trying to achieve this on Earth. So whereabouts can you get this sort of thing going on then that's common then? It's obviously in stars. So when you look at this, it goes on in stars like our sun. So this is the process that goes on in all stars, and you can see it in our sun here as a picture. So what we've got here is hydrogen and hydrogen fusing together and eventually forming helium. So if you look at this process then, we're talking about fusing two small nuclei together to form a larger nucleus, and there'll be a mass defect again, just the same as fission, given by E equals mc squared. That'll be the energy converted. So here's an example where we're doing deuterium, which is H21, joining with H21, and afterwards getting helium produced here, plus energy due to a small mass loss. And again, this is a very large amount of energy compared to typical chemical reactions. So nuclear fusion will occur when two nuclei get close enough together so that their short-range nuclear force that acts over very close distances can overcome that electrostatic repulsion and bind the two together. So when that happens, you're going to get a loss of mass there and energy produced. So that, as I said, they've got to approach each other at very high speeds, so they require high temperatures. So the sun and the stars are an ideal way of actually doing this. So the sun and the stars have an ideal location for this to happen because they, first of all, they've got a very high temperature, but not only that, they've got extreme gravity acting on them because of their large mass. And that gravity really just sort of pushes the two together and overcomes that electrostatic repulsion, getting them at a close enough distance for that short-range nuclear force to take place. So that's where it sort of happens. And we've talked about this idea that E equals mc squared is a conversion. Here's some examples of some of the sort of nuclear reactions going on in the sun there. So protons and protons are producing H21 deuterium plus a positron, and they're going on to join with other sort of forms here, protium plus deuterium, making this helium isotope here, plus gamma rays, so that gives you light. Okay, and you've got other helium nuclei then reacting with other helium nuclei to produce the normal helium that we've got here on Earth, plus more hydrogens to then start the process again. But there are many of these reactions going on in the sun. Most of it is hydrogen, and then a proportion has been now converted into helium. But the energy produced produces kinetic energy to the products, making the sun very hot and also releasing light in the process, and that's how we see it, and we get the heat as well. So for the sun and all stars, this is their method of actually producing light and heat. So here's a better picture of that process. Deuterium comes in with a proton and a neutron, goes to tritium, all right, and they fuse together, releasing energy because of the mass loss, and you're getting helium produced as a product and a neutron. So you could actually draw that as a H21 plus H31, your tritium, and in the nuclear reaction there we're forming helium-42 plus a neutron plus energy. Okay, so there's a balanced equation, 5 on the top, 2 at the bottom, and there's a typical sort of example of a nuclear fusion reaction that will go on in the sun. The advantage of having these deuteriums and tritiums involved in the reaction is you may not need to get it as close to actually get the reaction occurring. So you could do this at lower temperatures, because if you imagine these to sort of approach each other with the neutrons facing each other like that and the protons further away, this can get closer so that the nuclear force can take over with the protons still being quite a distance away, certainly further than if the protons approach each other as individual things. So this takes an awful lot of energy and therefore high temperatures if they're only just two protons fusing together. But if you're using deuterium and tritium, obviously the neutrons here sort of give it a bit of a distance between the two, and the nuclear force will act between the neutrons there. Okay. Now there are some key advantages with the fusion. First of all, the seawater here has got lots of deuterium in it. So I remember talking about having millions of years worth of deuterium in seawater that you could get from electrolysis. So you take the H2O, do electrolysis on it, and you can get your separation of hydrogen and oxygen and there's enough of the H21 version in there to actually supply our power stations for millions of years if we can get this to work. All right, so that's the first thing. We've got plenty of the fuel around, lots of fuel. Secondly, the product, if you look at this, is you end up forming helium as a product. So in terms of nuclear waste, the products of the process here are not radioactive, so therefore a lot safer. So we don't have that problem with fission where you've got radioactive products with long half-lives. So in terms of the fuel, it's better. In terms of the products, it's better. And it actually has a slightly higher energy yield per mass as well compared to fission. So this is the way we want to go. So if you look at these advantages, the best fuel, deuterium, H21 is found in seawater, and this says here 1 billion years worth of energy, but I can't remember if that's correct or not. The fuel is easy to extract from water, and the byproduct is oxygen, so it doesn't require this big mining process. The waste product helium is not radioactive, so there's no nuclear waste in that regard from the products there. And you don't get the same fear of meltdown because you do not need to get a chain reaction going for this to occur. You can shut this down relatively quickly without any sort of dangers going on. So we are working with high temperatures though, but only small amounts of plasma at a time, and you can control that very well. Okay, the total energy is quite low at any one time, not enough to be dangerous like the nuclear reactors we use at the moment. And as I said, fusion actually gives more energy per mass than fission, and you can show that with a binding energy per nucleon graph, which we no longer do. Now there are some key disadvantages here. It's very difficult to contain this plasma because it's so hot, and it's also very difficult to get it to that temperature and maintain it at that temperature to keep it going, unlike the location of the sun here where you've got high gravity and high temperatures. So they tend to actually sort of contain it in a magnetic bottle, because what you've got in a plasma is moving charged particles of electrons and nuclei. Okay, and those charged particles, when they're in motion, can have a force exerted on them by a magnet. So they normally create a magnetic bottle of some sort of shape there to try and actually contain it. So we actually tend to use a tokamak now, which is actually like a donut shaped magnet where that contains it inside, because if it touches the sides of a steel container, it would just melt straight through them. So we've got to contain it, we've also got to get it to that temperature and keep it at that temperature. So it's been very hard to successfully do that and get more energy out than what we put in. When we can get past that sort of solution, then we'll be okay. Then we'll have our energy problems much greatly reduced by it. Okay. There has been an uncontrolled fusion reaction achieved in the form of the hydrogen bomb, but what we're trying to do here is actually have a controlled reaction to produce energy for society. All right. So this would be the idea here with the fusion reactor: some sort of a magnet generated by coils here in a donut shape. You'll get the plasma to about 100 million degrees Celsius and being contained by that magnetic field. Now, during the process of the nuclear reactions here, you find that neutrons are released then with high kinetic energy. They'll go through the walls and heat up water to steam, which will power our turbine generators, just like the other situations we use for coal and gas and nuclear fission. There'll be a helium bleed pipe there used to bring the helium in. So that's where we're sort of headed. There's also a photograph of this further down, and they've been trying many different versions of these for a long time. This is the ITER one that they're actually currently working on. Okay, thank you.